In this video, we're going to perform some operations on Taylor series. What that means is we're going to start with a regular Taylor series that we already know, and we're going to do something to it. And you'll see in the first example, that's all we're going to do. In the second example, you're going to see how that can be a really useful tool for finding out things that we otherwise would have no way of knowing. So let's start with this one. We are going to write the Maclaurin series, both the first four terms and also in sigma notation, for the sine of 3x squared. And it's not as clear as it could be, but that 3x squared is all inside of the sine. The way this works is if we know what sine of x is as a Taylor series, and we see that this is the composition of sine of x where you plug in something else into sine of x, in this case we plug in 3x squared into sine of x, we can just plug that 3x squared into the Taylor series for sine of x, and that works. So if you remember, the Taylor series for sine of x, we'll write the first four non-zero terms first, and then the sigma notation x minus x cubed over 3 factorial plus x to the 5th over 5 factorial minus x to the 7th over 7 factorial. And the general term for that just keeps going forever, and as we fill in the pattern, it's negative 1 to the nth times x, I don't really need that parentheses, times x to the 2nth plus 1 over 2n plus 1 factorial. That would be starting when n equals 0. Well, if I want to find the sine of 3x squared, first of all, that 3x squared, the quantity being squared, I might as well just square the whole thing. So this is the same as the sine of 9x squared. It's a little bit easier. And the idea here is that all we're going to do is say, all right, well, if this new function that we're trying to graph here is the sine, but instead of just taking the sine of x, we're going to plug in 9x squared, what I can do is take that 9x squared and just plug it in for every single one of these little x's in here. Every single one of those x's is going to become 9x squared. So instead of plain old x, it's 9x squared. Instead of plain old x cubed, it's 9x squared cubed over 3 factorial. Everything around the x stays the same. It's just the x itself gets replaced with a 9x squared. And so you can see how easy it is to do operations on the Taylor series if you already know the Taylor series. And it works the same way with the sigma notation. Everything else is going to stay the same. It's only the place where the x is that's going to be replaced by 9x squared to the 2n plus 1. And so that is the first four non-zero terms, and also the general, this is called the general term. Of the Maclaurin series. We're going to use, on our next bag of tricks, we're going to use the same idea as just performing an operation on a Taylor series by doing it one term at a time in order to learn, integrate something we couldn't have integrated before. So we just look at that integral. The integral, so just talk about the antiderivative here, not a definite integral, of t times the cosine of t to the 5th in respect to t. Well, think through our bag of tricks. We can try u substitution there, but that's not going to help us because the inside function is t to the 5th. I would need a t to the 4th out here in order to do u sub. Well, I don't have it. I can try and think of this as an integration by parts, the integral of a product But I run into the same problem there. I can't really, and the t is a great du, is a great u, I mean, because its du is nice and simple. But I can't really treat the cosine of t to the fifth as a dv because I can't integrate it. So that's not ideal. So I really don't know how to do this. So we're going to do it anyway. We're going to use the power series to do it. So here's our steps. We're going to start by writing the power series of cosine of t. So like we're gonna try and treat this as like just turn the integrand, into a power series, and then it'll be much easier to integrate it because it'll be a polynomial, and we can all integrate polynomials. So let's walk through the process. You'll see how it works. And by the way, in doing so, what I did here, I turned it into a definite integral, so that way we can kind of see what it looks like in the end. It accomplishes the same thing. You'll see the point of this is to get the antiderivative. So forget about the definite integral part for now. Let's look at that integrand. We'll start with cosine of t. And when you do these problems, I do want you to write it out like one step at a time. Cosine of t, we have this one memorized. It's 1 minus t squared over 2 plus t to the 4th over 4 factorial minus t to the 6th over 6 factorial. That's 4 terms, so that's enough. By the way, this should say the first 4 non-zero terms. And then we can write that as the general term. We know it's alternating, so it's negative 1 to the nth. And we know our t is being raised to the even powers, and our factorials are those same even numbers. Sorry, that should say 2n, not 2t. Okay, then using the same trick we used in the last example, we're going to plug in t to the 5th. So now we're going to write a power series for the cosine of t to the 5th. And you might be saying, wait, that's not the integrand. The integrand is t times cosine of t to the 5th. And you're right. We're not up to that yet. That's our next step. We'll do this one step at a time. So all I'm going to do is plug the t to the 5th in for t every time, just like we did in the last example with the 9x squared. So 1 minus, instead of t squared, it's t to the 5th squared, which is t to the 10th, 2. And instead of t to the 4th, it's t to the 5th to the 4th. Factorial minus t to the 5th to the 6th, that's t to the 30th over 6 factorial. And so we can see the pattern here. It's still alternating, but instead of t to the 2n, it's t to the 5th to the 2n, which we would multiply the 5 times the 2n. See, our pattern is t to the 10n, and it's still over 2n factorial because we haven't changed what's in those denominators. Now we can finish writing the power series for that integrand. It's not cosine of t to the 5th. It is t times cosine of t to the 5th. But t times cosine of t to the 5th is just cosine of t to the 5th with a t multiplied to every single term. Because if what we're doing is turning this factor into a polynomial, then it becomes t times blah, 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 this whole polynomial. And so to multiply it by t, we would just distribute to every term. And so that's what we're going to do. We're going to distribute that t to every single term. So instead of 1, it's t. Instead of t to the 10th, sorry, that should say t minus, not t equals. Instead of t to the 10th, multiply that by 1 more t. Instead of t to the 20th, multiply that by 1 more t. T to the 30th, multiplied by 1 more t. And so now when we try and write that as the general term for that, it's only the exponent on that t that's changed, and instead of 10t, we've just taken that instead of that 10n, we've just taken that 10n and multiplied by 1 more t, so we've added 1 to the exponent. Everything else is the same. Well, Now that we have the power series for the integrand, t times cosine of t to the fifth, just by plugging in t to the fifth and then distributing the t, well, another operation we can do one term at a time is take the antiderivative one term at a time. So what we can do is take the integral of t times cosine of t to the fifth by using the power rule on every single one of these terms. So instead of t, it's t squared over 2. Instead of t to the 11th, it's t to the 12th over 12 times 2. Instead of multiplying that out, I'm going to leave that 12 times 2 there, so we can kind of, it's easier to find the pattern later if we leave the individual components alone. The next one, instead of, we're going to take the antiderivative of t to the 21st over 4 factorial. Well, that's just a constant that stays. Minus t to the 32nd over 32 times 6 factorial. And so those are our 4 terms, and so we can sum it up using sigma notation. It's still alternating. And now our powers of t are not just 10 to the n plus 1, but because we've taken the antiderivative of each one, we keep adding 1 to the exponent because of the power rule. So it's 10 to the n plus 2. And that 10 to the n plus 2 is now going to be a factor in our denominator also because of the power rule for the power rule of antiderivatives. But everything else, that 2n factorial, is still there. And so that's the antiderivative of t times cosine of t to the fifth in respect to t, which means if we want to write that as a function of x, as an accumulation function, and that's what the second piece of the derivative of the directions are, now we can write that as the sum of a bunch of terms with x in it. Because we have the same thing evaluated, the same antiderivative of the integrand. See, I'm just copying exactly what I wrote in blue one step above, but this time evaluated from 0 to x. And what's nice about this, when we evaluate it from 0 to x, because for the second term, that t is going to be a 0. That t is going to be a 0. We are only going to be subtracting 0 from this whole thing. So it's going to be this whole thing evaluated at x. Remember, we're evaluating the t at x, so that becomes an x. Everything else is still the same. And minus that whole thing evaluated at 0 would just end up being minus 0. So we can ignore that. And so what we have here is just a quick summary, a list of all the things we can do to find a Taylor series. Number 1, we can equate derivatives. Start from scratch using the method we started the unit with, except of course now we'll use the shortcut formula. We're not going to write out p of x and p prime of x and p double prime of x and all of that because we know where all of that leads. We can use the formula to find the coefficients, and that's how we equate derivatives now. Or if our Taylor series that we're looking for is based on a known series, e to the x, sine of x, cosine of x, ln of x. We'll learn one more next class also. We can just plug in a variable into that. Like if we want e to the 7x, we could just take the regular old equation for e, which is 1 over n factorial times x the nth, and just plug in a 7x instead of x. That's if it's a composition. We have something to plug in. Or, like we saw in the last example with that t coefficient, if we want to, we can multiply an expression through a known series, meaning we can distribute something to every term of the known series. Or we can integrate, like we did in the last series, and that works also for derivatives. We can always find the derivative of something by turning it into a Taylor series and then finding the derivative of those Taylor series. That's a little bit less useful because we already really could take the derivative of anything we wanted to anyway. It's only the antiderivatives that are sometimes impossible to do using other methods, and that's where the Taylor series method becomes